So welcome to the session of Laplace Transform. So this session is actually in the second module. So although we have finished the third module regarding Fourier transforms and Fourier series, and this is a continuation of Fourier transform. Okay, so we have seen many signals like t1 u of t, e raised to at u of t, t u of t, so many signals. We have found that if you substitute such signals in the integration of Fourier transform, the integration will not converge or integration will not suffice, or that leads to infinity. Okay, so in that cases we have taken pain, or we have used the Fourier transform properties to find the Fourier transform of such signals. The reason is that such signals, two reasons are there. One thing is that if you substitute such a signal in place of x of t in the integration will not suffice, or as t tends to infinity, this signal tends to infinity. So if this signal tends to infinity, again the signal itself is an unbounded one, the integration will not suffice or converge, or the integration will not converge to a finite value. It may lead to infinity. So these are the reasons why we cannot substitute such signals in the Fourier transform equation. So although we have found the Fourier transform of such signal using Fourier transform properties, that is not the right way of doing things. So how to bring how to converge these integration, or how to bring back these signals to bring back the signal which is leading to infinity to 0. So the thing is that if we apply a converging factor, that is e raised to minus sigma t, if we apply or multiply a converging factor e raised to minus sigma t to the basic Fourier transform equation, things will change. That is, when we multiply such a thing, even though we have a signal which tends to infinity as t tends to infinity, so due to the presence of such a factor, as t tends to infinity, this signal e raised to minus sigma t tends to 0. So this will pull back the signal to towards 0. So that is the crux, or that is the main thing that we have to understand while we learn about Laplace transform. So the basic thing that why we are making, or why we are moving to Laplace transform, is that Fourier many such signals does not have Fourier transform, because the integration was only along the j omega axis. Okay, that was the prime reason. That is the prime reason why many integrations will not converge. Whereas if we have such a multiplication factor, have such a converging factor like e raised to minus sigma t, then the signals which didn't have Fourier transform will have Laplace transform. Okay, so that is the thing. So let me start from the equation of Fourier transform. That is, the two equations are well known, that is x of j omega and x of t. X of t is the inverse Fourier transform, and x of j omega is the Fourier transform of x of t. So if I take equation number 1 and multiply by the converging factor e raised to minus sigma t, the speciality I already explained, that is, if when t tends to infinity, and even if x of t tends to infinity, due to the presence of e raised to minus sigma t which tends to 0, the whole integration converges. So when I multiply such a factor, you can see that e raised to minus sigma t is being multiplied. So earlier there was only e raised to minus j omega t. That is why the x was a function of j omega. Now as we multiply this with e raised to minus sigma t, you can see that if I take minus and t outside, it becomes e raised to minus inside the bracket sigma plus j omega. So earlier it was only the function of j omega. Now it's a function of sigma plus j omega. Okay, now I substitute sigma plus j omega as s, which is called the Laplacian operator, and so sigma plus j omega can be replaced by x. So x of j omega becomes x of s, which is equal to integration from minus infinity to infinity x of t e raised to minus st dt. This equation number 3 is called the Laplace transform of x of t. Similarly, equation number 2. Similarly, we can substitute the converging factor e raised to sigma t there. So if you do that, and we can take t outside, it becomes e raised to sigma plus j omega, and x of sigma plus j omega d omega. 1 by 2 is obviously outside, and that is what is x of t. Now we have to change everything in terms of s. So we know that sigma plus j omega is s, or ds is nothing but sigma is a constant, and we are that is nothing but j d omega. So, or d omega is nothing but ds by j. So integration was with respect to omega. So when omega tends to infinity, s also will tends to infinity. When omega tends to minus infinity, s also tends to minus infinity. So the limits of integration will remain the same, substituting everything. So that j can be taken outside because integration is only with respect to s. So 1 by 2 pi j integration from minus infinity to infinity x of s e raised to st ds. So equation number 4 is nothing but the inverse Laplace transform. So that is how we evolve the Laplacian equations, or Laplace transform and inverse Laplace transform from Fourier transform. Okay, so the basic idea is to converge the signals which are not converging, otherwise converging, or converging the integrations which are otherwise not converging by multiplying by a factor e raised to sigma t. So minus sigma t is very important. So in any situation, this is a very important statement. In any situation, we have to take care to make sigma value positive. If sigma value is negative, then minus and minus becomes e raised to sigma t. So positive sigma means e raised to sigma t. That itself is a unbounded signal. That is, if t tends to infinity, that also tends to infinity. So we have to avoid situations where sigma is positive, sigma is negative. Sigma is negative means the entire thing becomes e raised to sigma t, which is again an unbounded signal. So there are situations where Laplace transform also does not exist, and that is a situation, that are situations when sigma becomes negative. When sigma becomes negative, the integration will not converge. So we have the convergence of the Laplace transform basically depends upon the value of sigma, or value of sigma means real part of s. What is real part of s? S is nothing but sigma plus j omega. So real part of s means sigma. So the real part of s, the value of real part of s, or the value of sigma will actually decide the convergence of Laplace transform or existence of Laplace transform, and that is coined with a name called region of convergence. So what is region of convergence? So as I told that it all depends on sigma value or the real part of s. So the Fourier transform we found, that is x of j omega, that is integration was only along j omega axis. Now we can see that sigma is a real part adder. Only initially for Fourier transform there was only j omega axis. Now we have added sigma also. So sigma has its bounds towards the positive direction and also towards the negative direction. So we have an entire S plane. So this is called the S plane. What you see on the right hand side is nothing but the S plane. Okay, so S plane can have so many points. Okay, so the x of s integration will be along the entire S plane. So instead of j omega axis, integration along the j omega axis, which was the case in Fourier transform, we have integration all along the S plane in Laplace transform. The points in the S plane where the integration converges is called the region of convergence. So the points where the points in the S plane where the integration converges. Integration convergence means integration result is less than infinity. That is called the region of convergence. So a convergence or ROC, because there are points in the S plane where integration does not converge. For those signals, Laplace transform does not exist. So earlier itself I told a statement. So what are those points? Those are points where real part of S or sigma value is negative. So when sigma value becomes negative, or that is the value of sigma which makes e raised to minus sigma t e raised to plus sigma t. So if Laplace transform does not exist, or if there are points in the S plane where the integration does not converge, the meaning is that there are values of sigma which makes e raised to minus sigma t e raised to plus sigma t. That is why we are so particular about the value of sigma. So it all depends on the real part of S or the value of sigma. So these are the things which we have to keep in mind. I have taken an example here just to make you understand. That is, a range of sigma or real part of S for which the Laplace transform converges is called the ROC. Just the definition once again. Then consider a signal x of t which is equal to e raised to 2t u of t. This signal otherwise does not have the Fourier transform, because you can just see that e raised to 2t is an unbounded signal, because as t tends to infinity, e raised to 2t also tends to infinity, and that is shown in the figure, in the first figure. That is, it also leads to infinity. Whereas if we multiply such a signal x of t with e raised to minus sigma t, and if you take so we already have e raised to 2t, and then we are multiplying the whole signal with e raised to minus sigma t. If you take t common, it becomes e raised to 2 minus sigma t u of t. So that actually converges. That also, as t tends to infinity, that tends to 0. So you can see that how long that will converge. E raised to 2 minus sigma t u of t, how long that will converge? That will converge only for values of sigma what greater than 2. So if sigma is less than 2, for example, if sigma is 1 is less than 2, what happens? It becomes e raised to t. E raised to t is again a unbounded signal, all that tends to infinity. Whereas if sigma is greater than 2, for example 3, then that is e raised to minus t. So the condition is that that is sigma value or real part of S should be greater than 2 in this case. If it is less than equal to 2, then again that is 1. 1 is again, if you integrate with from minus infinity to infinity, that also tends to infinity. So 1 can also, so 1 is not at all acceptable. So that is e raised to 0t is also not acceptable. That is, sigma value should be always greater than 2 in this case. Okay. Whereas if it is equal to 2, again that does not converge. If it is less than 2, that is 1, 0, everything, all those things will make the signal towards infinity. So in this case, the real part of S or sigma value should be greater than 2. That is why I told that for this integration to converge, the real part of S or sigma should be greater than 2. For all other points, or all other points in this plane, the integration does not converge. So that value of sigma will decide the region of convergence. Okay. Now, existence of Laplace transform, the foremost and first condition is that the integration, if we want to apply integration, the signal should be continuous, or at least piecewise continuous in the given interval. Okay. Then the usual statement, that is second point, x of t must be absolutely integrable. That is, when you do the integration, that is, absolute integration means the modulus of x of t e raised to minus sigma t dt, that should be less than infinity. If that is not less, that tends to infinity, then that integration does not suffice or converge. Then we are considering a particular case, that is unilateral Laplace transform, that is one-sided Laplace transform. And we start with causal signals. What are causal signals? Causal signals are signals which are multiplied with u of t. If a signal is accompanied by u of t, then that is a perfectly right-sided signal or a causal signal that does not have values for t less than 0. That will be having only values from t is equal to 0 towards infinity, or t greater than or equal to 0. So let us take the first example. If we are multiplying a signal with u of t, the integration from minus infinity to infinity becomes from 0 to infinity. That is why that definition of x of s is there. Okay, so the first question is, what is the Laplace transform of an impulse function, that is x of t is equal to delta of t. So if you apply that, this integration, even if you apply from minus infinity to infinity, this integration will have delta of t this integration will have only a value at t is equal to 0. So that is e raised to minus st at t is equal to 0. When you substitute t is equal to 0, e raised to 0 is 1, and 1 is for all values of s. So even if we substitute any values of s, the value is equal to 1. That is why, irrespective of value of s, the value is 1 for the Laplace transform of delta of t is nothing but 1 for all values of s. So a region of convergence is all the points in the s plane. It includes all the points in the s plane. That is for the impulse function, or it is nothing but the entire region of convergence. Entire S-plane. We can take region of convergence of an impulse function as the entire S-plane. Now second case, that is u of t. U of t otherwise does not have the Fourier transform, even though we have found the Fourier transform by the help of Fourier transform properties. So if you substitute u of t is nothing but 1 from 0 to infinity. So it becomes simply e raised to minus st dt. If you perform the integration and apply the limits, then you will get it as 1 by s. So this integration will only converge when real part of s is greater than 0. You can just imagine what is s. S is nothing but sigma plus j omega. So if sigma is equal to 0, then again you are making e raised to minus sigma t, which is e raised to minus sigma t equal to e raised to 0. And if you are making sigma as minus 1, then you are making e raised to minus sigma t as e raised to plus t. So all those cases are not at all acceptable. We have to keep that convergence factor as such. Okay, so the only condition for the convergence factor to keep as such is nothing but the real part of s should be greater than 0, or sigma should be greater than 0. So you can one more point I have to make is that 1 by s, that function has a pole that is at the origin. So you have a pole at the origin. So for this one, the region of convergence will be towards the right side of the pole, or the region of convergence. That why the region of convergence is towards the right side of pole? Because your real part of s, that is the sigma value, should be greater than 0. Equal to 0 is also not acceptable. It should be greater than or greater than 0. Or you can say that the region of convergence is towards the right side of the pole. And one more point, very important point I like to make, is that the region of convergence does not include the pole. Region of convergence does not include the pole. Why does this does not include the pole? If it includes the pole, then real part of s equal to 1 should also be acceptable. That is not acceptable. So real part of s is greater than 0. So the pole is not at all included in the region of convergence. So the region of convergence is right side of the pole. Now in the same vein, if you consider ramp function, which is t into u of t, if you apply everything, you will get it as 1 by s square. Again the same thing, that is real part of s greater than 0. And similarly, if you apply the parabolic function x of t is equal to t square u of t, here also for third and fourth problems, you have to apply the integration by parts. You have to learn, go back and take 11th standard textbook, math textbook, or you can browse and see what is integration by parts. This you have to learn. This you have learned in the +2 classes. You are applying the integration by parts here, and again you can see that the result is 2 by s cube. These are a very important result. You have to by heart also, because you have to apply these results in the problems coming. So again you have to write the result in that form, that is t square u of t, bidirectional arrow above that lt stands for Laplace transform, 2 by s cube. So ROC is nothing but the real part of s greater than 0. And then a typical problem, fifth problem, it has many applications, that is real exponential function, that is e raised to at. A is a real function, that is why we have a real exponential function u of t. This also otherwise does not have a Fourier transform. This signal itself will not converge, because as t tends to infinity, this also tends to infinity. If you apply that, and if you take the common things outside, that is minus and t, we can write it as integration from 0 to infinity e raised to minus s minus at dt. Okay, and if you apply the integration and apply the limits, and you will get it as 1 by s minus a. Here you can see that the pole is at s is equal to a. The pole is at s equal to a. And here you can see that the integration will converge only if real part of, earlier it was real part of s. Now instead of s, we have s minus a. So here the real part of s minus a should be greater than 0. Or you can say that real part of s should be greater than a, or sigma should be greater than a. Or you can see that that is a is the pole here, so the region of convergence will be towards the right side of that pole, that is a. Okay, so here you can see that the j omega axis is not included in that ROC. Okay, and that has a significance. I'll tell that just now. That is, similarly, if it is e raised to minus at u of t, that has definitely has Fourier transform, because that signal is a converging signal. And if you perform the Laplace transform, you'll get it as 1 by s plus a. And here you can see that this Laplace transform will converge for real part of s. What is a pole here? Pole is nothing but s is equal to minus a. So it will converge for real part of s greater than minus a. So you can see that the region of convergence is towards the right side of minus a. So earlier it was towards the right side of a. Now here it is towards the right side of minus a. And what is the difference? I told in the earlier problem, that is e raised to at u of t, that it does not include the j omega axis. And the second question, I told that the signal itself is converging, it has Fourier transform. Obviously we have found the real, we have found that also. What was that? It was a plus 1 by a plus j omega. Okay, so here you can make a statement that if the region of convergence, you have found the Laplace transform, and if we have a question whether the signal has a Fourier transform, this is the answer for that. That is, if the region of convergence includes the j omega axis, such signals have Fourier transform. I repeat, if the region of convergence includes the j omega axis, such signals will definitely have Fourier transform. And vice versa. That is, if the region of convergence does not include the j omega axis, such signals will not have Fourier transform. Just like e raised to at u of t, which does not have Fourier transform. Here, e raised to minus at u of t, as it includes the j omega axis, will have Fourier transform. That is a very important point to note. Okay, and then the complex exponential function, that is x of t is equal to e raised to j omega t u of t. If you substitute, you will get e raised to minus s minus j omega t dt. Here j omega is actually the imaginary part, so we are only concerned about sigma value, or the real part of s, or the result is 1 by s minus j omega. Here also the region of convergence, as we are concerned only with sigma value, region of convergence will depend on the value of sigma, or we can say that real part of s greater than 0 is the region of convergence. So e raised to j omega t u of t, Laplace transform is 1 by s minus j, region of convergence, real part of s greater than 0. Similarly, you can write it as e raised to minus j omega u of t, Laplace transform is nothing but 1 by s plus j omega, where region of convergence is a real part of s, or sigma value greater than 0. Now, the last one, that is sine and cosine functions. If you have a signal like cos omega t u of t or sine omega t u of t, then how do you do that? We'll take cos omega t u of t, and we know what is cos omega t. Cos omega t is nothing but e raised to j omega t plus e raised to minus j omega t whole divided by 2, and we have u of t that is being multiplied. And if you take half outside, and if you apply the Laplace, if you try to find the Laplace transform of e raised to j omega t u of t plus half Laplace transform of e raised to minus j omega t u of t, the result is already available. E raised to j omega t u of t, we know what that is, 1 by s minus j omega. And e raised to minus j omega t u of t Laplace transform is also available, that is 1 by s plus j omega. Take half outside, manipulate it, and you will get it as s by s square plus omega square, where again you can see that it is all about exponential complex exponential functions. So again, we are not concerned with j omega, we are only concerned with real part of s. So here also the region of convergence is a real part of s greater than 0. So similarly, you can find what is sine omega t u of t. Sine omega t is nothing but e raised to j omega t minus e raised to minus j omega t by 2j. If you apply that and find the Laplace transform, you will get it as omega by s square plus omega square, where again the ROC is a real part of s greater than 0. So these are very important results, and which we will apply very frequently in the problem session. And next, tomorrow's class will be the problem session, where we'll discuss some numerous cases, typical examples which are very important in exam point of view. So you have to prepare notes and repeatedly see this video, so that you'll understand Laplace transform in a better way. Okay, thank you.